couple of them from the data structures and algorithms program, and a couple more quantum talks or quantum related talks. And the first talk will be given by Bento Natura on fast exact solvers for LPs.
Yeah, thank you. I'm visiting from Georgia Tech. And let me jump right in to a problem that is very much related, or say at the core of my research. And that is a special case of linear program, a classical problem that we all know, and that is bipartite matching. So far, no weights, just easy. We have bipartite graph. We have on one side workers A, on the other side tasks B, and we want to assign workers to tasks subject to, at most a worker being assigned to at most one task, and we want to maximize the tasks that are fulfilled. Very classical problem. How efficiently can we solve this problem? And the first question I'm asking is, okay, how fast can you do it in the number of edges of your graph? And in terms of L, where L is the bit complexity of the numbers appearing in my input, but here they are not really numbers, so L is 1. And the answer is, okay, we can do that in this polynomial running time, and classic, it's 70 years old. Okay. Can we do it in almost linear time in terms of the number of edges in our graph? And that is a very recent breakthrough result. Yes, we can do it. I think Sushant is even in the audience here. Okay. And now what I'm often interested in is, can you drop the dependency on the bit complexity? Now here, there is not really bit complexity. I mentioned that already. So in fact, the above is already an algorithm that solves the problem in runtime that is polynomial in the number of edges. Okay. Now let's turn it into a weighted problem. Now all my edges have weights. So we have certain costs to assign workers to tasks. And these costs are, say, integral for our purposes. And now it changed a bit this constraint here to say I want that all tasks are assigned, and subject to that, I want to minimize the cost. Classical weighted bipartite matching problem. How efficiently can we solve it? First question, okay, can we solve it in running time polynomial and the number of edges and the bits? Now the bits are meaningful because my costs can be arbitrary. And it turns out we can do it. Again, classical algorithms, just Edmonds Carp as an example. Can we do it in linear time, subject to still having dependency on the bit complexity? And the answer is yes again. This is, again, the breakthrough result from last year. Does apply again. Okay. Now, can you drop the bit complexity on L? Because this result here has a running time that is logarithmic in the size of C. And the answer is, again, yes. And there are, again, many classical algorithms. The Hungarian algorithm does it. Orleans algorithm that is more general for min-cost flow does it as well. So here we can solve that problem in quadratic time. Okay, now let's add another twist to the problem, also classic, but less studied. And that's the following. Also, all my edges now have efficiencies. So let's say not all workers are equally efficient to fulfill a certain task. No, some people are specialized in something. And now these efficiencies are just numbers that are non-negative. And now I want to, again, assign workers to tasks fractionally such that all tasks are fulfilled. Where fulfilled means now that if I assign an XAB fraction of a worker to a task, then a gamma X fraction of the whole task is fulfilled. Okay, now this makes it a bit more complicated. Now, how efficiently can we solve that? Again, running time polynomial in the number of edges and bits. Yes, we can do it, but now we need a bit more heavy machinery, namely, it's a linear program, and linear programs can be solved in running time in general. That is polynomial in the number of edges, or polynomial in the number of variables and the bits. Okay, can we do it in almost linear time? And the answer is no. We don't know how to do it. And now the question is, can we do it without depending on the bit complexity of my problem, so without depending on the cost and the gain factors? And this is very recent result of us that we can actually do that in so-called strongly polynomial time. In fact, it's a bit more general, but this will come in the next slide. And I'm happy to give a long talk here in the semester on this. Unfortunately, I'm the organizer of the seminar. So you have many seminars, so maybe someone else can invite me to their seminar to give the talk there. Okay. Yeah, so this was a special case of a linear program. And the story is a bit different for people who like dependency in the bit complexity and for people who don't like it. For me, I'm more in the don't depend on the bit complexity side of it. And if you like dependency in bit complexity, then you can do it in polynomial time. you can do it very efficiently, almost optimally, in the sense that you can almost do it as fast as linear system solving in certain instances, up to dependency on the bit complexity, of course. But on the other hand, it is not known whether there's a general strongly polynomial time algorithm for LP where you would drop the dependency on the bit complexity. Okay. What we know is that you can solve it in strongly polynomial time if my matrix is nice in a certain sense. So if all my entries are integral and not too large, where this is a very generous definition of too large, the entries are allowed to be up to 2 to the poly n. Okay. And now the new result is that we can also solve in strongly polynomial time if every column contains at most 2 non-zeros. So this is a bit, actually it's vastly more general than what I had on the last slide, because it would apply not only to bipartite graphs, but to general graphs, and also not only for directed graphs, but also for undirected graphs. So yeah, that is the result. Okay. Yeah.
To need AB polynomial, the polynomial in the size of A. Size of A is included in B.
Yes.
Right. So
yes,
is there a generalization to something based on, say, separation oracles?
Can you make this question more precise, please?
Well, you said it applies to non-bipartite graphs as well.
Yeah. I mean, just forget about graphs. Just think of a matrix that has at most 2 non-zeros per column.
Yeah. All right. Well, I don't want to hold you up. Go ahead.
Okay. Yeah. And now there's the slide that Yinyu showed last time, and I'll just write a new update to this now. So if you're interested in strongly polynomial algorithms versus weakly polynomial, then what did we have before last year is all these classical combinatorial problems, and a few more. Let me not explain them here. People who work on these know their definitions, of course. And also when we are on small dimension, and it turns out that there is one algorithm that is strongly polynomial for all of these. And there were 2 special classes that we don't know yet how to solve in strongly polynomial time. One is general Markov decision processes, and one was the 2 non-zero entry per column problem. And now I can move this to the solvability to the class that is solvable, which brings me immediately to the open problems that are still there in the area, and that is, of course, can you solve MDP in strongly polynomial time? And beyond that, I would be interested in the following problems. There is this gap now since last year between strongly polynomial solvers and weakly polynomial solvers that is linear. So even for single source shortest path, when you have negative edge weights, then Bellman-Ford is the best thing you can do to solve in strongly polynomial time, which is order mn. In weakly polynomial time, we've seen the result in order m. There's even another paper that is more combinatorial that also achieves order m. For the minimum cost flow, the same story. Even if it's, in theory, it should be more complicated than single source shortest path. In both worlds, weakly and strongly polynomial, they have the same running time as single source shortest path. So can you break this linear gap between weakly and strongly polynomial? And this question you can generalize to general LP. If I allow sort of a bit complexity dependency on the constraint matrix, but not on my objective or my right-hand side, then what you can do in general is that if you have a class of linear programs that you can solve in running time that is some function of the dimensions and the number of non-zeros, and then is polynomial in the bit complexity of A, B, and C, then you can turn this into a strongly polynomial time algorithm that does not depend on the bit complexity of B and C anymore, but now has an additional quadratic term in running time. So mn comes in the front of it. Of course, we see that for graph-based problems, this gap is linear, but here it is quadratic. So a question would be, can you reduce this quadratic gap to something that is smaller? Okay, and I guess I'm at the end of my talk. Thank you.
You have time for a couple of questions?
This was the question Phil was asking. What kind of access are you assuming to A? Like, is it like separation oracle, or are you?
Oh, A is given to me explicitly.
Explicitly.
Yeah.
Can you, which of these things go through if you have just like separation oracle?
It's hard to do things exactly when you only have a separation oracle. So I haven't thought about that. Yeah.
Cool. Thank you.
Thank you. This was a very nice overview. Can you tell me, if I understand correctly, with more than two, let's say 3 variables per column, it's as general as any.
Exactly.
Is that
Yeah.
that believed or known?
Oh, it's the same as you can sat reduce to 3 sat. In the same way, you can reduce any LP by quadratic blow-up or cubic blow-up to an LP with 3 variables per inequality. So 2 is the most you can hope for before you solve the whole problem.
Super. Yeah, thank you.
Any other questions?
So the problem you solved is not solvable in linear in the number of edges?
We don't know.
You don't know?
We
Okay.
don't know. Yeah.
I see. Thank you.
All right. Thanks again, and let's move to the next.